The Hercules-Corona Borealis Great Wall stretches 6 to 10 billion light-years across space. This structure is so massive that light takes longer to cross it than Earth has existed, yet astronomers debate whether this cosmic giant even qualifies as a real structure. The question reveals a deeper mystery: what actually limits how big things can get in our universe? Every telescope upgrade reveals larger cosmic structures than scientists expected. The 1980s claimed the universe became uniform at 100 million light-years. The 2000s pushed that boundary to 200 million light-years. The 2010s stretched it to 300 million light-years. Each discovery forced astronomers to rewrite the rules about cosmic architecture. Today's largest catalog structure challenges our understanding of what holds the universe together. The measurements come from gamma-ray burst patterns, galaxy surveys, and dark matter maps. But the real question isn't just how big structures get. The deeper puzzle concerns whether these cosmic giants are actually structures at all. Galaxy clusters represent the first rung on the cosmic size ladder. The Coma cluster packs over 1,000 galaxies into 20 million light-years of space. Located 300 million light-years away, Coma contains massive amounts of invisible dark matter detected through X-ray observations. These X-ray emissions reveal superheated gas trapped between galaxies at temperatures of millions of degrees. The Virgo cluster sits much closer at 52 to 54 million light-years and dominates our cosmic neighborhood with over 1,300 catalog galaxies. Virgo's gravitational pull affects the motion of our own local group, dragging us through space at hundreds of kilometers per second. Superclusters initially seemed like the next size tier, but modern surveys complicated this picture. The local supercluster spans 100 to 200 million light-years but lacks the gravitational binding astronomers expected. Recent analysis by Van de Wegaert's team revealed the local supercluster as a concentration along filaments rather than a self-contained system. The Shapley supercluster, 650 million light-years distant, contains roughly 25 major galaxy clusters with thousands of member galaxies. This cosmic behemoth exerts gravitational influence across vast distances, creating what astronomers call the Great Attractor Effect. Redshift surveys transformed our view by mapping galaxy positions in 3 dimensions. The Sloan Digital Sky Survey mapped 1 million galaxy redshifts by 2012, revealing the cosmic web's true architecture. The 2-degree field galaxy redshift survey added another 220,000 galaxies to the map. These surveys showed galaxy clusters arranged along filaments separated by enormous voids. The cosmic web resembles a 3-dimensional spider web with galaxies concentrated along the threads. Filaments typically extend 100 to 200 million light-years. These cosmic highways contain roughly 60% of all galaxies in the universe. Voids span 100 to 300 million light-years in diameter. At scales beyond 300 million light-years, the universe appears statistically homogeneous. The Buddha's void stretches 330 million light-years across while containing only a handful of galaxies. Astronomers nicknamed this region the Great Nothing because of its almost complete emptiness. Dark matter comprises 80 to 90% of the mass in these large-scale structures. Baryon acoustic oscillations create a characteristic scale of 490 million light-years in galaxy distributions. This scale represents the imprint of sound waves from the early universe, frozen into the cosmic web like ripples in cosmic ice. The Hercules-Corona Borealis Great Wall currently holds the record as the largest known structure. Horvath's team discovered this cosmic giant in 2013 through gamma-ray burst analysis. The structure sits 9.2 billion light-years away at redshift 1.6. Its extent measures approximately 6 to 10 billion light-years across, though measurements vary between research groups. The Great Wall consists of a loose filament of galaxy clusters and superclusters rather than a gravitationally bound object. To visualize this scale, imagine the entire observable universe shrunk to the size of Earth. The Great Wall would stretch from New York to Tokyo. Gamma-ray bursts served as tracers because they outshine entire galaxies and can be detected across cosmic distances. These stellar explosions release more energy in seconds than our Sun will produce in its entire lifetime. Horvath's analysis found statistically significant clustering of these cosmic explosions. The team analyzed hundreds of gamma-ray bursts to map the 3-dimensional structure. Keenan's group challenged the discovery in 2016, questioning whether the clustering represents genuine structure. The debate centers on whether loose associations of galaxy clusters constitute real structures. Critics argue the pattern might be a statistical artifact rather than a physical object. Supporters maintain the clustering exceeds random chance by significant margins. The controversy highlights a deeper problem in defining cosmic structures. Galaxy clusters are gravitationally bound and will survive cosmic expansion. These systems will remain intact even as space itself expands around them. Superclusters and great walls are not gravitationally bound and will eventually disperse. The Great Wall will stretch and fade as dark energy accelerates cosmic expansion. Redshift space distortions complicate size measurements by distorting apparent galaxy positions. Peculiar velocities of galaxies create artificial elongation along the line of sight. Correcting for these distortions introduces systematic uncertainties in claimed sizes. The Sloan Great Wall, measuring 1 billion light-years in extent, previously held the size record before the Hercules-Corona discovery. Each new survey pushes the boundaries of what astronomers consider possible. The observable universe boundary creates an absolute limit on structure size. The particle horizon extends 46.9 billion light-years from Earth in co-moving distance. No gravitationally bound structure can exceed this physical constraint. This boundary represents the maximum distance light could have traveled since the Big Bang. The cosmic microwave background reveals the seeds of all cosmic structure. Planck 2018 measurements show structure grew from 0.1% density fluctuations at recombination. These fluctuations occurred 380,000 years after the Big Bang. Angular scales of 1 degree in the cosmic microwave background correspond to 180 million light-year scales today. The microwave background acts like a baby photo of the universe, showing the tiny wrinkles that would grow into galaxies. Dark matter provides the invisible scaffolding for all large-scale structure. Without dark matter, ordinary matter lacks sufficient gravity to build cosmic architecture. Computer simulations like the Millennium Simulation and Illitris project reproduce observed structures reasonably well. These digital universes require supercomputers running for months to simulate billions of years of cosmic evolution, but the exact physics governing filament geometry and void sizes remains incompletely understood. Dark energy affects structure evolution by accelerating cosmic expansion. This mysterious force opposes gravity and prevents new large-scale structures from forming. Future surveys from the Vera Rubin Observatory and Euclid mission will refine these measurements. The end-of-greatness problem continues to challenge cosmologists. Each decade brought discoveries of larger structures than theory predicted. Some researchers like Pietranero argue the universe may have fractal-like structure at larger scales. Mainstream consensus favors homogeneity by 300 million light-years, but debate persists. The definition of structure remains contested among astronomers. Gravitational binding provides one criterion, but statistical overdensity offers another. The Hercules-Corona Borealis Great Wall fails the gravitational binding test but passes statistical significance. This definitional ambiguity affects how scientists count and compare cosmic structures. Future deeper surveys may reveal even larger patterns or confirm current limits. The James Webb Space Telescope and upcoming ground-based observatories will probe deeper into space than ever before. The universe's largest structures push against both observational limits and theoretical understanding. The Hercules-Corona Borealis Great Wall represents the current size champion at 6 to 10 billion light-years across, but its status as a true structure remains scientifically contested. The cosmic web's filaments and voids create patterns on scales approaching the homogeneity limit. Dark matter provides the hidden foundation supporting all cosmic architecture. This invisible substance outweighs ordinary matter by 5 to 1 throughout the universe. Future surveys will either discover larger structures or confirm we've reached the cosmic size limit. The next generation of telescopes will map billions of galaxies across cosmic time. The debate reflects deeper questions about what constitutes structure in an expanding universe. Gravitational binding, statistical significance, and observational artifacts all complicate the measurements. The answer to how big structures can get depends as much on definition as observation. Each new discovery forces astronomers to refine their understanding of cosmic organization and the fundamental forces shaping our universe. What seemed impossibly vast just decades ago now appears as merely the first glimpse of architecture on scales that challenge our very conception of cosmic order. The universe continues to surprise us with its grandeur, pushing the boundaries of human imagination and scientific understanding.